Now, in this talk today, I would like to give you a few perspectives on galaxy formation simulations, looking a little bit back at the current state and also making some potentially provocative statements about the future prospects to steer some discussion. So let me maybe start with this on my title slide, with this first simulation that I'm aware of from 1941 on galaxy collisions by Erich Hohenberg. He used light bulbs, 37 of them, to represent basically galaxies, and measured then with a photodiode the gravitational field, here the light field, and then moved by hand every one of these light bulbs to compute a galaxy collision. And he got, already tidal arms in that. So that is quite amazing. From that point on, it took us 40 years to arrive at the first cosmological simulations. Carlos alluded to them, by the Gang of Four. And it was George Estafio who wrote the code for that. In fact, this paper by him is just 40 years old and has his birthday this week. And this was really introducing myself. For example, studying that paper was an eye-opener for how to do cosmological simulations. And that was the 80s, right? And it still took us from that 40 years more to arrive at simulations of galaxy formation that can actually resolve Milky Way-sized disks. So that's now sort of current work, here led by Rüdiger Packmore and Francesca Fragudi, who simulate, in cosmological simulations, the formation of Milky Way-sized disk galaxies. And here you see just the stars for a relatively short time, close to the present-day universe. This is fully embedded in a 100 megaparsec cosmological volume, and these are simply cutouts that focus on the stellar disk. And what you notice here is that we can do now galactic dynamics problems, for example, bar formation, fully embedded in a cosmological volume. And these galaxies have structures that are very similar to observed systems. So we have come a long way in making galaxies, especially considering that 10 years ago, all the cosmological simulators couldn't make any galaxy, this galaxy yet, right? The disk galaxy formation was always a big problem. So we have made a lot of progress. And now I'm going to show you the simulations in 40 years from now. This is going to look like this. So we'll then have, of course, a good census of the star-forming regions, and also we'll get the dust lanes correct, etc. This is, of course, cheating. So this is how HST sees a galaxy. So we would like to understand, of course, all these processes. And as I will argue in my talk, we have these fantastic simulations. We have, I would say, a backbone theory for galaxy formation that works. But yet, galaxy formation itself isn't really solved. Now, cosmological hydrodynamical simulations of galaxy formation, they have one distinctive, huge advantage compared to other types of calculations you can do. They start from initial conditions that are very well specified. And Neil just described, of course, the observation from the CMB. And so the idea of these research is basically to take that on a supercomputer and evolve that precisely specified initial state forward in time. In that sense, these simulations link also cosmological large scales to small scales in astrophysics. And I think this linkage is crucial to actually test whether this somewhat bizarre model, right, where we have dark matter that we don't really know yet and dark energy, whether this makes any sense, right? So I think this type of work better produces objects like the ones we have in the real universe. Otherwise, we really would have to question whether our fundamental physics picture can be correct. Now, let me comment a little bit on the present state in the field. So there are many groups now very successfully simulating galaxy formation with hydrodynamical cosmological simulations. They broadly fall into categories of two kinds. We have Zoom simulations on the left and large cosmological boxes. And Julian already described and reviewed the work very nicely earlier in the week. So I will now refrain from explaining all of the differences between the different types of works, but it's a very active field where really very rapid progress is still being made. I briefly want to describe a highlight from my own work, which is the Elastistine G project from a few years back now already. These were 3 cosmological boxes. 3 because in that way we can combine the results and basically cover a larger range of scales, both small galaxies and also very massive ones for which you need large volumes to find them. Now here, maybe a movie for the simulation is instructive at this point. This shows a large-scale region, actually a protocluster region here. The gas flow is visualized, and you see here is quite a lot of actions ongoing. It's relatively turbulent. Occasionally, you see flows emanating from very small regions in space. This is actually because there's a galaxy in a supermassive black hole that accretes, and it expels material over large cosmological scales. In fact, I think this scale coupling that AGN are able to do is probably the most extreme I'm aware of. Very small scales affect very large scales. It's a very difficult problem. And there's also an emergent phenomenon of these bimodal flows of this galaxy that has become active here again. It's bimodal, even though the feedback we put in on very, very small scales is completely isotropic. So this is an emergent phenomenon that these flows appear in this way. And we're blending over to the stellar distribution. So there are in this protocluster hundreds of galaxies falling together. And these calculations are able to, of course, follow the interactions and how gravity, for example, tightly strips these galaxies, how you assemble intracluster light. And you have, and that's a crucial aspect of this calculation, you have, of course, the full time evolution. You can connect mock observation at different times in a way that is not easily feasible with observation. So that's, I think, one of the power, of course, of cosmological simulations to be able to do this and look at these calculations, not only in the stellar component, you can look at the dark matter component, you can look at the diffuse gas, at the optical light, at the magnetic fields, at the thermal conduction, and all sorts of aspects. And just to give you a flavor of some results really quick, broadly speaking, these calculations have become very successful in ELASTIS-TNG, but also from the other groups. They make many galaxies of all shapes and sizes. And the morphological mix matches the galaxies we see, to first order at least. The sizes, for example, for late-type galaxies and early-type galaxies match observational sizes. This is really a non-trivial finding. We reproduce the bimodal color distribution of galaxies and as a function of stellar mass and the appearance of a red quenched sequence for massive galaxies, late times. This is a result due to AGN feedback. Without it, we would not be able to explain that. And the galaxies not only have the right stellar masses and colors, they also sit at the right places. The clustering pattern of galaxies that we see in the local universe is reproduced very well. And the pattern of the cosmic web is a very strong constraint, also cosmological parameters, of course. Here you see a comparison between ELASTIS-TNG results in red and epsilon size survey data. And this also works if you split the galaxy population by color, for example, in red and blue systems. There are small discrepancies here and there, but I wouldn't consider them particularly seriously. So, I think it seems to me highly contrived if all of this data, and I could show you now many, many more plots of agreements with mild tensions here and there. But broadly speaking, it's amazing that the simple picture that we have, with these still relatively coarse calculations, is able to match such a huge, diverse range of data on galaxies. And that's also why these calculations have, I think, a huge impact now in the field. For ELASTIS and ELASTIS-TNG alone, more than 1,000 papers have already been written using the data, right? And you literally see a paper on ELASTIS-TNG coming out at least, several, usually every week. So that's quite an important impact on the field. Yet, the group, that's the whole ELASTIS team, right? This is 10 people. So such a small team, it's kind of a blessing to work with this. If you compare the complexity, many of you will be in observational teams. DESI has 1,000 people, Euclid maybe 2,000 people, right? So this is really difficult. So it's nice to be in a small theoretical team like that. On the other hand, the relative sizes of teams also informs a little bit about the relative funding this work gets, right? And I think theory is really dirt cheap compared to our observational missions, and actually I think we should do more of it because of that. Now, what is the physics in galaxy formation that we have to follow? So the basics is you need to follow gravity, right? Gravity pulls together material to make galaxies, and here the dark matter is governing most of it. So we need to do collisional gravitational dynamics of the dark matter in large stellar systems. This is something we can do very well. So the methods are very well understood. All the codes agree on that. We also need to do ideal hydrodynamics to follow the diffuse gas flows. The methods for that are also well understood. They have more numerical defects usually, so one has to work a bit more on that to make them still more accurate, but I think this is also understood, and we understand very well also how to set up initial conditions and put the cosmological background. So that part is kind of under control. What we then have to add is astrophysics for galaxy formation. And these are here illustrated in these little ellipses here. So gas cooling, for example, multi-phase interstellar medium, and you have enough resolution. Star formation, of course. Stellar feedback processes, the metal enrichment, it comes with stellar evolution. Then we have supermassive black hole growth, and its feedback. And also we have radiation fields, we have magnetic fields, cosmic rays, and then maybe transport processes in plasma. So this is a lot, right? So it's a complex astrophysics, which you all have to somehow include. And that's what these codes try, to various degrees of approximations. And here's a color key in this. So I think the green parts, I think are roughly doable. And at least there's maybe less controversy about them. The yellowish things are, I also think, more or less doable if you have enough resolution. The problem are the red parts here, which is really complicated stuff, and that's where so-called subgrid modeling is key, and subgrid treatment is a necessity, right? It's often frowned upon, but I think it shouldn't. But of course, it brings in huge uncertainty, and that's what we have to work on in the future. It's one of the challenges to reduce the uncertainty that comes with that, to actually solidify these predictions from these calculations. So let me then talk about some opportunities that come from that. So first of all, I would argue that galaxy formation is not solved. I mean, despite I've advertised a little bit the success of so many of these works, but I think many, especially the small-scale astrophysics, is not solved at all. And so I think we need to keep working on it. And as simulations keep getting more powerful, there are obviously lots of opportunities to continue working on the small-scale frontier of galaxy formation simulations. For example, we would like to do large galaxies with resolved ISM and individual supernova explosion. So Thorsten has given us a very nice talk how this is already attempted, in small galaxies in isolated systems typically, but we want to roll this out in larger systems in cosmological simulations. I think this will be forthcoming in the next years. We want then, with that, clarify the physics that drives galactic winds and outflows. And Christoph, for example, talked about cosmic rays in this context. That's something that is important to understand because we put in the winds by hand, essentially, nowadays, to make the small galaxies faint enough. And that's a critical thing you need to do, and especially in cold dark matter cosmologies, where there's just a huge abundance of small halos that are not materializing in a steep faint end in the galaxy luminosity function. So you have to explain why star formation is extremely inefficient. This can only be achieved by expelling a lot of baryons. So we need these galactic outflows. We don't know how they are really made yet. It's a huge gap in our understanding of galaxy formation. Obviously, we want to not ignore the radiation fields anymore. They are now first very promising attempts to do this, for example, in the context of cosmic ionization. We have, for example, in the TSON project where this is done and included self-consistently, but it's very expensive. Jim alluded to this, and it's also expensive with coarse approximations even. So, but we'll have to address this in the next years. And then maybe the biggest boogeyman in the room is, the black hole physics, which has the enormous challenges in the dynamic range, and we heard from Jim about the leading work in that, really looking very close in with GIMHD calculations. This is not something we can expect to do anytime soon in a cosmological simulation, probably never. So we'll have to connect these calculations together and use the small-scale work to inform next generations of more accurate cosmological simulations. Other things like dust formation evolution, we have already such models, but they don't really work yet to a satisfactory degree. So we'll have to fix those, and I think that seems maybe doable, even though also that is actually quite messy stuff, messy physics. And finally, there are aspects like And body dynamics, Thorsten mentioned that in his talk and showed results of leading work there. The black hole orbits and the interactions of black hole binaries. This is a crucial phenomenon that is regulating the growth of black holes. Maybe when they are displaced by gravitational wave recoil, we need to understand how soon they return to galactic centers and so on. So that is not yet captured well enough in the cosmological simulations to then, for example, make reliable predictions for, say, LISA for the event rate of these mergers of supermassive black holes. Now, some of these opportunities are really enabled by computing, and Jim really introduced this very nicely yesterday, and the exascale computers that have been arriving now in the US, they soon be available in Europe as well. 10 times exascale is already being discussed. What I will argue now, also later in my talk, is that to really benefit from these machines in astronomy, we need suitable codes to run on them. That's not a small part of the issue here, actually. So we have the machines, but we don't necessarily have the capability, except, Athena K, if Jim's problem, he can do it, but, cosmological problems are not yet as far and cannot use these machines yet. But suppose we solve that, then we can really address grand challenge astrophysical theory problems. I think, for example, I would really love to do a cosmological simulation of the Milky Way, where we have a solar mass resolution or better, with a fully resolved interstellar medium. And then studying the meta cycle between the intergalactic medium, the circumgalactic medium, and this interstellar medium in a realistic way. That is very interesting, very important, I feel. The origin of supermassive black holes at high redshift. We have this exciting new developments with JWST. Has always been a pressing problem, and it has only become more timely to think about that. So there are just a few examples. And I think there are more. And I think the challenge is, again, it's to a significant degree on the code side, whether we can do this on the available supercomputers now. And there are also some large-scale frontiers, and that relates basically to what Risa talked about. So we need better theory models for galaxy formation, and direct hydrodynamic simulations are playing an important role here. With these mega surveys, we would like to use galaxy clustering, weak gravitational lensing, for example, to really constrain the standard cosmological model, put it to the test at sub% level, find cracks in it potentially, find, for example, evidence for non-standard cosmological constant, evolving dark energy. And to do this, really the missions need much better simulation models also, right? We need, Risa explained this, we need theoretical predictions, very large volumes. If you want to do this directly with a hydro simulation, say, or with an n-body simulation, you need 1 trillion particles minimum, gigaparsec boxes, and these are very big simulations, very difficult to do. Right? Now, we have recently done a first project in this direction where we combined the illustrious TNG with our older Millennium simulation in the same volume. We've done a Millennium TNG. This is a 15 times larger hydrodynamical simulation than illustrious TNG 300. And then we went even bigger to a 1.1 trillion calculation, dark matter only, but with neutrinos, with a 3 gigaparsec box. So that's something we've done recently, and with this much larger volume, we can then study with very high precision various large-scale structure problems. This, for example, galaxies on the light cone out to redshift 2. We also have neutrinos in this calculation. So here is another light cone where actually we sit here in the center. We look out to redshift 2, left and right. And here is the neutrino density field on top. In this model, we have 2 degenerate 50 milli-electron volt neutrinos, so its some rest mass is 100 milli-electron volt. You see that at redshift 2, the neutrino density field is still very smooth. But as the velocities redshift away, they start to cluster in the biggest large-scale cluster, clusters of galaxies and superclusters, and enhance also their structural growth. Now, the hope is that the future galaxy surveys will be accurate enough to detect the consequence of this on structure formation. So in the meantime, we can now predict, for example, how neutrino masses will impact things like the cosmic star formation rate history. Here you see at high redshift, there are 30–40% effects minimum, and also in the galaxy luminosity function. On the right, there is a comparison of different models with 0 neutrino rest mass, 100 milli-electron volt and 300 milli-electron volt, and you see that the massive models, they give you at sort of in the tail of the mass function, of course, rather large changes now in the galaxy stellar mass function. So that's one of the handles, and there are more. You can look at the baryonic impact on, say, weak gravitational lensing maps, and then look at the angular power spectrum of that. You see effects that come here from the baryon physics. This is, again, the AGN impact. These other lines here are for the neutrino impact. So you have to basically consider both to get really accurate predictions. We can, for the first time, measure intrinsic alignment with extremely high signal to noise. So this is important for weak gravitational lensing. It's an important contaminant. That is our measurement here in red. And you see the arrow bars. So previous generation of hydro simulation that did not have the statistical power to detect this with this enormous signal to noise ratio. So that comes directly from the shapes of the stellar systems, and it's the intrinsic correlations of the galaxies. Now let me, in the last couple of minutes, talk about some of the real challenges that I see. Now the first one is the sizes of these calculations have, of course, exponentially grown, from modest sizes, in the 80s or so, now to 1 trillion particles. That comes with large data volumes, which are painful to work with, really. And this most recent simulation that I showed you has 2.5 petabyte in size. Of course, the radio astronomers know that type of data volume, right? But they also have professionally run data centers that we don't have in theory, right? So we have to do this all ourselves, again, with a team of 10 people. So that's a challenge. And the other is, a multi-scale, I would call this the multi-scale challenge, because if you think about this, galaxy formation really combines a huge range of scales, about 20 orders of magnitude. From cosmological scales down, in principle, a supernova explosion that regulates our star formation, there is a thermonuclear flame front of a few centimeters is important, right? You cannot represent all of this in a single calculation evident. There will always be a subgrid scale somewhere, right? And so that but then it's actually worse. If you think about it, often people, when we don't like a calculation, I'm often asked, why does your resolution suck so much? Why don't you run this with higher resolution, right? So if you increase the spatial resolution by a factor of 2, you also need to reduce the time step by a factor of 2. It means that if you don't change anything else, the computation cost of your model will go up by a factor of 16. So that means if you just want to push down by 1 decade here, then the computation cost of that by a factor of 10 improvement in spatial resolution is 10,000, right? You need 10,000 times the number of computational cycles for that. So that is actually very effectively eliminating any progress in technological hardware, right? Because if you assume Moore's law for your processor, which is not really actually working anymore now for computation speed, while it still lasted, the computation speed doubled every 18 months of a core, you would have to wait 20 years to get this factor of 10,000, right? So that's actually sobering in a way. On the other hand, what's alleviating this problem is there's parallelization and local time stepping and adaptive zoom simulation and so on. So there are various tricks you can play to get around it. Yet, this is a fundamental problem that it's very hard to actually do a multi-scale calculation for a long time. In addition, there are current trends in HPC that maybe tell us that, Jim was very upbeat that zeta scale is coming soon. I'm much more pessimistic about this for various reasons, because, a trend that we have seen for a while now is that individual compute cores don't get faster anymore, get many more of them. There are now these heterogeneous architectures with accelerators, and that requires a level of concurrency to use parallelization that is just staggering. You have to spread your calculation on millions of parallel compute threads. Very difficult to do. But another trend that's also not very pleasant is that the 64-bit double precision floating point performance that we rely on, that actually sees no improvements anymore. It stagnates right now because all the chip makers invest all the development money in low precision arithmetic for AI. We really are not of interest at all anymore for that. So that's another casualty of AI boom. And there's the performance of the communication backbone. Of course, energy costs also set a limit, right? So you have to, this is the machines now are at the upper envelope of what's possible. Yet, we have fantastic machines now. Frontier is the first exascale machine fastest machine in the world right now. LuMi-G is the fastest in Europe. It's exactly the same architecture as Frontier, but only 1/3 of the size, right? So you can apply for time on these machines and use them. And we're getting also in Europe an exascale machine. The first one will be Jupiter. It's being built right now. Just to give you a perspective, what this costs, this stuff, 500 million euro is this leading edge machine roughly. But you know, astronomy gets only a few % of these resources, right? So it's still actually very modest cost for the field as a whole to do that. Now this, just to give you a flavor of why it's difficult to program for these exascale computers and other modern supercomputers. Well, a compute node nowadays is not composed of just compute cores like it used to be, but now there are these heterogeneous architectures where you have several, you know, no ordinary CPU basically, and then you have, this case, graphics compute dies or GPUs attached to it, 8 in this case, and the compute power is based in these things. And they have, on this one node, there are 56,000 cores that you would have to use in parallel and keep busy all the time in a parallel thread. Unfortunately, they are not all independent, but 64 of these threads have to do the same instruction all the time. So that is, you want to get the maximum performance, you have to do this. So that is actually quite hard to do, right? And on Frontier, it's of course similar. You have in total 500 million of these threads on the full machine. So 500 million. So you have to expose a huge degree of parallelism if you want to use this machine. It's very difficult to do for tightly coupled problems that we tend to have in astrophysics. Yeah, and you know, I think the software is a little bit the problem. I think that's the challenge here, and it's often, I would feel, it's a bit underappreciated. And to raise your awareness for this, let me show you how my own codes evolved since the times of my PhD. So I wrote a code in my PhD. This was still possible, 8,000 lines. This was the gadget code, and this was in 2001. 2005, this had swelled to 18,000 lines. We did the Millennium simulation with that. Then in 2010, we changed to a repo that was 160,000 lines at that point. Now in 2018, when we did the Elastis TNG calculation, it was 330,000 lines of code. Now we are at 480,000 lines of code. Now an incoming graduate student has to deal with this, right? We haven't changed the way we work since 2000, right? So the supervisors think, oh, just give, you know, they give this, here are the 408,000 lines of work. No, in 2 weeks, come back with the first results, right? And I think we can't do this because anymore, probably in the future, in this sort of completely, in a way where we think these codes come out of thin air somehow, right? So and you know, it's in this analogy, on a telescope, you need an instrument. You have large instrument building groups that are well funded to build this. The supercomputer, the theoreticians have to write a code, which is the equivalent, but there's no systematic support for that. Now, finally, on this sort of provocative side of my comments, let me finish with some sociological remarks as well. I think currently we also have maybe a real problem in educating a next generation of researchers who would like to do such calculation and also have the skills to do this. Of course, everyone uses computers all the time, and the students are extremely good often in Python. This favors development speed over computation efficiency, which is great because it's, human development time is precious. It's much more precious than CPU cycles, but it's not an ideal preparation of getting into the mindset of writing efficient HPC code, obviously. And in addition, I think it's more fashionable to believe now that the future lies in AI rather than in solving partial differential equations. At least that's my impression when I talk to people. So, and maybe we don't have to lift the finger anymore, right? I'm often asked, do you code yourself still, or is it all ChatGPT? And I think that we still need to train students in astrophysics and high-performance computing if we want to unlock these opportunities that I tried to describe. So, thanks a lot.